Right, hello again, everyone. It's good to see you all after a fairly significant break. Once again, we're going to have Ben Andrews talking to us. He's going to continue his discussions on the two-dimensional Ricci flow. Thanks, Ben.
Thanks, Tim. Yes. So the last time I talked about the case of negative Euler characteristic or positive genus and the zero genus case, and that works out relatively straightforwardly. The case which is most difficult is the case of metrics on the sphere. So I'm going to talk about that today. So let me just remind you a bit what we're dealing with here. So we have this 2D normalized Ricci flow, and this is just the equation that ddt of the metric.
I can't see your screen.
Yes, I think you may have.
Yeah. Hold on a sec. Let me try that again.
Yep, good.
Is that better?
Yeah.
I don't know, I didn't connect the first time. Okay. There we go. I'm just going to move this here. All right. Yeah. Okay. So the Ricci flow. So the normalized flow is just this one. It's just a conformal flow where the rate of motion is Gauss curvature minus kappa. And here I might as well just take kappa equals 1. So it'll be on the sphere. So we'll just take kappa equals 1 times Gij. Okay. And so we know that this corresponds to just a scalar evolution equation for the conformal factor. So if we write, say, G equals e to the 2u times some whatever reference metric we like, then this just becomes the scalar equation. Du dt is e to the minus 2u times Laplacian with respect to g bar of u minus Gauss curvature of g bar, and then plus 1 coming from the one in the equation. So unfortunately, in this case, looking at that scalar equation really is very hard to get any good intuition for what happens. And it's the argument that I gave last time using the potential function gives you one thing in this case. It gives you, okay, I'm going to just recap. Last time we proved, we looked at this potential function. So this is defined by Laplacian of f is equal to Gauss curvature minus kappa. Okay, so you can solve this because Gauss curvature minus kappa is integral 0. And then using that function, we get this nice estimate that, ddt of gradient f squared plus essentially curvature, so twice Gauss curvature minus kappa, is, so we get a nice evolution equation. We get a Laplacian term, we get a 2 kappa times the same thing, and then a negative term, so we say less than or equal to that. And so that gives control in the case, that's a kappa there. In the case kappa less than or equal to 0, this gives a really nice control on this gradient f squared plus curvature. In particular, it gives a curvature bound. And that was sort of the key to proving existence there, proving convergence there and long time existence. If kappa equals 1 here, then this doesn't give us a time independent bound, but it does give us an exponentially growing bound. So this, in the case kappa equals 1, this still tells us that we have, kappa, the Gauss curvature bounded by some, some constant times e to the 2t or something like this. So we do have at least bounded curvature for all times, and so we have long time existence. So this normalized Ricci flow we know does exist for all t. Okay, but that's about all we can get out of that at the moment.
Hey, Ben.
Yeah.
I wondered if you could perhaps zoom in a bit. It might just be my terrible eyesight, but I think I'm finding everything a bit smaller than what you did last time.
Let me see what I can do. Yeah. Is that better? Maybe
Yeah,
try that.
yeah, that's great. Thanks.
All right. Okay, so what can we do in the positive curvature case? So let me start off by just reminding you about where this quantity came from. Right? So this quantity here that we looked at, gradient f squared plus 2 k minus kappa, was motivated by these so-called Soliton identities. Okay, so here you suppose that you have a soliton solution. So these are special solutions of the flow, and these would be things which satisfy Hessian of a function plus k minus kappa gij equals 0, and that's really the same thing as the rate of change of the metric is given by the Lie derivative of the metric in the direction of gradient f. So any metric which satisfies this would in particular give a nice solution of this normalized Ricci flow, which doesn't change geometry, it just changes parameterization. Okay, and then so this implies, of course, just by taking the trace, this Laplace f plus 2k minus kappa equals 0. So that was the equation we used to define the potential function. And then we also showed that by differentiating that equation 1 and commuting derivatives, that we get this nice equation for the gradient. So gradient of Gauss curvature minus Gauss curvature times gradient of f is 0. Okay, and then from that we got this identity which motivated the estimate up there. So this said that gradient f squared plus 2k minus kappa should be just 2 kappa f plus a constant. So this sort of conserved quantity here. There's a couple more identities which I didn't mention last time, which I want to mention now. At least these only make sense in the case where you have Gauss curvature positive, or at least maybe non-zero. So this equation 3 tells me that the gradient f is really just the gradient of log k. Okay, so, and now if I differentiate that, I get gradient I, Hessian of f, is the Hessian of log k. Okay, and then identity 1 becomes, so 0 equals gradient I, gradient j log k plus k minus 1 gij. Let me go back to the case kappa equals 1 here. So I'm going to call that quantity qij. This is sort of a matrix. So this now no longer depends on the potential function, right? So this depends only on the curvature. And then if I take the trace of that, I also get 0 is Laplace log k plus 2 times k minus 1 is 0, and I'll call that q. So it's just a trace of qij. So these other two quantities, which also sort of come from this soliton characterization. So somehow the vanishing of these things would correspond also to the fact that it's a soliton equation. It takes a little bit of work to go back in the other direction, but certainly a soliton has to have qij equals 0 and q equals 0. Okay, so there's a nice observation that comes from that, which this is Hamilton's Harnack estimate. So it's a differential Harnack estimate, which really means a Lie-Yao type estimate. Okay, and this is motivated by that these quantities, the q and the qij. Okay, so the claim is that under this normalized Ricci flow, in the case Gauss curvature positive, ddt of q is Laplace q, and then I'll get a plus twice qij squared, and then I'll get a plus a 2q. So it's 2 kappa q. Okay, and so it's a beautiful, simple equation. In particular, this is greater than or equal to this norm of qij squared would be greater than or equal to a half of q squared. So I get this inequality here, and that gives me a very strong lower bound on q. So that would be just from the maximum principle. This would imply that the q is at least, so is it -2 over 1 minus e to the minus 2t. Okay, so essentially as t becomes large, it's got this kind of nice lower bound, stays away from 0. Okay, so that's the differential Harnack estimate, the Lee-Yao type estimate. To prove that, actually, I'm going to use, there's an interpretation of Q, which is rather nice, which is this. So ddt, okay, so first of all, the curvature itself, the Gauss curvature, evolves by this equation. So we have ddtk is Laplace k plus 2k, k minus 1. Okay, and this somehow is the equation which causes all the trouble, because we've got this, basically this k squared term here is sort of an uncontrollable growth. So that could cause it to blow up in finite time. Now we kind of know that doesn't happen already from the potential estimate, but that's the part that causes all the difficulty. So in particular, what I want to get is a bound on the Gauss curvature, which is independent of time. And there's sort of 2 steps in doing that. The first one is this Harnack estimate, and the second I'll get to in a moment. Okay, but so from here I get that ddt log k. Okay, so then I just divide through by k. So I get Laplace k over k plus 2k minus 1. And that first term here is almost Laplace log k. Okay, Laplace log k would be Laplace k over k minus gradient k squared over k squared. Okay, so this would be, it's Laplace log k plus gradient log k squared and plus 2k minus 1. Okay, so that almost looks like q, right? So this is q plus gradient log k squared. Okay, well, turning it around, there's an interpretation here, which is that q is the rate of change of log k under a kind of modified flow which is, okay, so I'm going to take the normalized Ricci flow, but then I'm going to reparameterize. So I'm going to throw in the Lee derivative in a direction, and the direction here is indicated by this term here. Okay, so if I rewrite this, it says that Q is ddt log k minus gradient log k in the gradient log k direction. Okay, so that means it looks like ddt log k, except that I'm also moving, I've got a gradient as if I'm moving in a spatial direction in direction log k, gradient log k. Okay, so the modified flow should be ddt gij is what I had before, minus 2k minus 1 gij, but then I should also have the Lee derivative in direction gradient log k of g. Okay, so what does that mean? Well, of course, we know what the Lee derivative is. It's just the Hessian now of log k. So this would be minus 2k minus 1 gij. And now I'm going to get, well, so it'll be 2 times the Hessian. So it's minus 2 gradient I, gradient j log k. So that's a modified flow. Doesn't look a lot like Ricci flow anymore. In fact, if you looked at it just from a purely PDE point of view, then, well, log k actually involves 4th derivatives. This Hessian of log k would involve 4th derivatives of the metric. So it's a kind of ugly looking equation, but you should remember that this is really just Ricci flow in disguise with a reparameterization. So I'm not going to worry about existence of this as a 4th order PDE. We start with a solution of Ricci flow, and then we reparameterize, and we get a solution of this thing. But the nice thing is that this is now just minus 2 qij, right? So this is exactly the quantity that I wrote down up here, gradient Hessian of log k plus k minus 1 times g. So that now becomes the rate of change of the metric under this modified flow. And we also have under the modified flow ddt log k. Well, so this should be the same as it was before, except that now I'm adding in the flow in the gradient log k direction. So log k direction. So this is exactly q. Okay, so this is now the system describing this modified flow, equivalent to the normalized Ricci flow. All right, so now I want to compute ddtq using this setup. Okay, so ddtq. So this is ddt of Laplace log k plus twice k minus 1. And all right, so that's relatively straightforward to do. So the Laplacian, okay, so I did this before, I guess, in the last time. So the Laplacian you can write as 1 over square root of determinant g derivative in the ith direction of square root of determinant g inverse ij times the j derivative, all that times log k. Okay, and then plus 2k minus 1. The k minus 1 I can throw away. It's just 2k. All right, so then I get one term where I differentiate the log k. So that'll be just Laplace ddt log k, which is Laplace q. Okay, so that's differentiating here. Then when I differentiate the determinant of g, well, the ddt of the determinant is going to be the trace times the determinant. So that'll give me a minus 2q. So that would give me, and I've got a 1 over the square root of that. So I'm going to get a plus q Laplace log k. Okay, so that's differentiating that first square root of the determinant. Then differentiate the stuff that's inside the derivative. So I get gradient I of the square root of the determinant is going to give me a minus q gij, and that's the derivative of the gij is going to give me a okay, so that's differentiate the inverse of the gij. So I just get plus 2 qij, and then I have a gradient j log k. Okay, so here, where are these coming from? So this determinant here gave me this term. This determinant here gives me this term, and differentiating this one gives me this qij. Okay, and then I get the ddt k at the end. So ddt log k is q, ddt k is k times q. So I end up with plus a kq, sorry, 2kq from that last term. All right, so that's not too bad. So if I put those together, first of all, the plus q is fine. The q times Laplace log k plus 2k is almost a q squared. All I'm missing is so if it was Laplace log k plus 2 times k minus 1, that would be a q squared. So I just have to take that off again. So here I'll get a q squared plus 2q. So that's those two terms. And then I get, so these other terms, I'll get, okay, so let me just rearrange that. So I get a 2qij minus qgij times gradient j log k. And then I'll get terms where I differentiate those, which is minus gradient iqgij, which I'll just write as gradient jq, plus 2 gradient iqij, divergence of q, gradient j log k. Okay. All right, so this works out relatively nicely, and it's partly because everything here is a soliton quantity. And so we know that if this was happening on a soliton, every term that we get has to be things that vanish on the soliton. Right? So we're differentiating tensors which are 0 in that case. So So the time derivative has to be things that are also zero. So they have to be soliton quantities. So that's really explaining why we're getting all these soliton quantities coming up in this evolution equation. All right, so there's one term here which I need to expand a bit here. That's this term here. So if I go to the definition of Qij, so remember that was just gradient I, gradient j log k plus k minus 1 Gij, and I differentiate in I direction. Okay, so I'm getting a gradient I log j. So it'll be Laplacian gradient j log k. And here I'll get just a gradient I k times Gij, which is gradient jk. And now if I commute the derivative past the Laplacian, this will be a gradient j Laplace log k plus gradient j k minus 1. And then I got another term from commuting past, which is just another gradient j k minus 1. Okay, so the nice thing is that's just gradient jq. Okay, so that actually turns out quite nicely. This minus gradient jq plus twice divergence of qij is just a plus gradient jq. Okay, so then we're pretty much done. So what we end up with is that we get Laplace q plus q squared plus 2q. Then this 2qij gradient I gradient j log k is going to give me a plus 2 qij squared, okay, because this Hessian here is most of a qij. And then I'll get a minus q, so that so this qgij times this is just a minus q squared. So minus q squared, and that will cancel this one. Yeah, and then the last term just became a gradient log k times gradient q. Okay, so everything works out rather nicely. So there's the evolution equation under this modified flow. But just applying the maximum principle to that, I straight away get that q is greater than or equal to, because this last term is just a gradient term. The same arguments before said that q has this nice lower bound under the modified flow. So it's minus 2 over 1 minus e to the minus 2t. But now this modified flow is just Ricci flow reparameterized. So if this quantity q is greater than this function under the modified flow, then it's also got the same lower bound under the normalized Ricci flow. So, so the same is true under the normalized Ricci flow. Okay, so that's this beautiful Lie-Yao type inequality. Now I should explain, why is it a Lie-Yao type inequality? Q is, as I said, almost ddt log k, right? So Q is ddt log k minus gradient log k squared is greater than or equal to this right-hand side. Okay, so it's that is really that's the Lie-Yao type differential Harnack inequality. Okay, all right. So we're going to show you later how we use that. Roughly, yeah. So roughly speaking, this is saying that the kind of have a lower bound on the time derivative, saying that it's okay. Apart from this constant on the right-hand side, it's essentially bigger than the square of the spatial derivative, and we can integrate that up along curves to say that if the Gauss curvature is big somewhere at one time, then it's big in a whole region on a later time. Okay, we're going to use that to get our curvature bound. All right. So in order to do that, well, we have to. Yeah, so what we should be able to do from that is say that we get a large, if the curvature got big at one point, at one time, then if we wait a little bit of time, the Harnack estimate would say that we'd have a whole region on which the curvature is large. And we contradict that by trying to get a bound on some integral of Gauss curvature. Okay, so that's this entropy estimate. All right, so we're just going to look at the quantity which is the integral over m of Gauss curvature times log Gauss curvature, okay, with respect to the volume element given by the metric g. It gets called entropy mostly because it kind of looks like an entropy under, you know, in the sort of classical systems where you have an integral u log u, something like that in the heat equation, for example. Apart from that, you know, there's not really a good entropy type motivation for this. But let me compute the time derivative of this under the Ricci flow. Okay, so ddt of n. Okay, so what do we know? The first of all, I just differentiate this with respect to k. This is going to give me a 1 plus log k times ddt k, which is Laplace k plus twice k minus 1. And then I also get a ddt of the volume element. Okay, so k log k times ddt, the volume element, is going to be minus 2 k minus 1. Okay, so it's integral of all of that with respect to the measure. All right, so what can I do with this? First of all, the this Laplace k term I can integrate by parts. And that will give me, okay, so the derivative is going to hit the log k, so I'll get a gradient k over k, got minus integral over m, gradient k over k dot gradient k, so this is just gradient k squared over k. Okay, and now the other nice thing here is that the terms involving logs, okay, I've already dealt with this Laplacian one, but the other ones I get a 2k minus 1 log k. Sorry, that wasn't quite right. This is 2k k minus 1 here. Yeah. So I get a 2k k minus 1 log k from this term, and that's exactly cancelled by this contribution from the volume element. So then the only term that's left is this one with the 1 out the front. Right? So that will give me a plus 2 integral over m k times k minus 1. But remember, k has also got mean value 1 because we're on the sphere. Gaspard theorem. So this is the same as 2 integral over m k minus 1 squared d mu. Okay, so it's a relatively simple looking evolution equation for this entropy. So this is sometimes called the Hamilton entropy. Quite different from the Perelman entropy. In particular, only makes sense in the case of Gauss curvature positive, right? So that's one important difference. All right, so claim is that this right-hand side is less than or equal to 0. In fact, strictly negative unless the metric is a soliton of the Ricci flow. Now, Hamilton had a kind of bizarre proof of this in his paper, which is quite unlike anything you'll see anywhere else. What he showed was that if I take the second derivative of ddtn, okay, so what would that mean? So the first derivative, essentially roughly, if I didn't do these integration by parts, I would get in ddtn, I would get things like ddt Gauss curvature, right? And then if I differentiate again, I'm getting ddt Gauss curvature, which is like our quantities Q here, sort of the Harnack quantity. So if you plug in the calculation we just did for the Harnack into there, and then integrate by parts, you get this kind of bizarre thing that the second derivative of n is greater than or equal to some multiple of the first derivative squared. And integrating that up, you could show that if dn dt was positive, that it would blow up in finite time. But we know the thing exists for all time, and so that can't happen. And therefore, dn dt has to be less than or equal to 0. yeah, anyway, so that for a while that was the only way people knew how to prove this entropy was monotone. But I'm going to show you a very different argument, which I think actually explains a lot better why that's true. Okay, so the claim is that dn dt is less than or equal to 0. In fact, let me prove something slightly more generally. On a compact 2 manifold with positive Gauss curvature, if we have any function with integral 0, then we have this sort of Poincare type inequality, which says that the integral over m of gradient f squared over k is greater than or equal to twice integral over m of f squared. Okay, so for the Ricci flow case, we would apply this with f equal to k minus 1. All right, so proof, and in fact, there's an equality statement too. Let me put that in. So equality holds if and only if there exists, let's say, a little f such that f times gij plus Hessian of little f is 0. Okay, so what's the interpretation here of this equality statement? This means that if I do conformal change of the metric by the function f, then that is really the same as reparameterizing the manifold in direction of some function gradient f. Okay, so what that really, in a sense, that's saying that the capital F is just the metric change generated by some conformal deformation, conformal reparameterization. Okay, so proof. Well, the reason I wanted to mention that interpretation is that the way we prove it is actually using these soliton type identities, right? So if I start with this equation here, then I get another identity, which is the trace of that, which is Laplace little f plus 2 times big F is 0. And then I can also play the same games as I played in the Soliton case by differentiating equation star and then commuting derivatives. It's essentially the same computation that I did before. And that would tell me that the gradient of big F, so, okay, what happens if I take gradient of F and then I get a third derivative of little f, then when I commute, I'm going to get curvature times gradient f, and the curvature is just written in terms of the Gauss curvature in this case. So the result we get is gradient of big F is Gauss curvature times gradient of little f. Okay, so we get these three equations here in the case where this soliton equation holds. All right, and now I'm just going to do a nice little integration computation. So I'm going to take each of those quantities. Okay, so gradient I, gradient j, little f plus f gij squared, integrate that over the manifold, and take away the integral of Laplace f plus 2f squared, and then add on the integral of, okay, so I'm going to take essentially the square of this gradient quantity here, except that that has to be there with a factor 1 over k. So gradient I k, gradient I f minus k gradient I little f squared. All right, so what will that give me? Just going to expand things out. I'll get Hessian squared of f plus 2 integral of f, and I get gij times Hessian of f, so it's a Laplace little f. And then I'll get a f squared, big F squared times the gij squared, which is 2. So this is 2 integral f squared. Then I'll get a minus integral Laplace f squared. Okay, and the trick is, of course, it's well known there's close connection between integral of Hessian squared and integral of Laplace f squared. So we're going to do an integration by parts trick to relate those two. Then I'll get a -4 integral f Laplace f, and then I'll have a -4 integral f squared. And in the last term, I'll get a plus integral gradient f squared over k. Okay, that's going to be giving me this term in our inequality. In the cross terms, the Gauss curvatures cancel out. So I'm just going to get a -2 integral gradient f dot gradient little f. And then I get the last term, which would be plus integral Gauss curvature times little f squared. Okay. So, well, lots of nice things happen. These three terms in the middle are 0. Okay, so, I mean, the first two I end up with a -2 integral big F Laplace little f. Integration by part is going to cancel out this other term here. So that's 0. These two terms here, as I said, if I wrote those out and do an integration by parts, then they're actually the same as each other, except I have to commute derivatives, and that's going to give me a curvature term. So in fact, those two, together with this curvature times gradient little f squared, also give me 0. Okay, so what I end up with is this exactly the combination which I want. So this is gradient f squared over k, and then I get -2 integral f squared. Okay, so what can I do? So I have all this stuff on the left-hand side, but now given big F, again with this assumption that the integral big F equals 0, I can solve Laplace little f plus 2 times big F equals 0. Okay, and then plug those into the equation. Right? And so in that case, I get, well, the left-hand side, I get a positive term, the first one. The second term is 0 because I've chosen little f to solve that equation, and the last term is positive. So I get the left-hand side is greater than or equal to 0, and therefore, the right-hand side is greater than or equal to 0, and that's our inequality. Yeah, so it's beautiful Poincare type inequality. This actually implies, if you think about it, the lower bound on the first eigenvalue of the Laplacian on a manifold with positive Gauss curvature in 2 dimensions. Right? So it says that essentially it's bounded below by the 1 over k, right? If I can bound the 1 over k from below, so it's yeah, I need a lower bound on Gauss curvature to give that. Okay, so there we are, and the equality case also we get from that, because if equality was to hold, then all these terms on the left-hand side would have to vanish, and so in particular this term here would have to vanish, okay, which is what the claim was. Okay, so there we are. That's the fact that ddt n is less than or equal to 0, and that's some kind of integral curvature bound. Right? It looks a little bit weak. In fact, I should point out here, we always know that integral of Gauss curvature is bounded because that's just Gauss finito. So integral Gauss curvature is always going to be just 4 pi or whatever. So this n sneaks in just a little bit more control here, this log k, and that will be enough. Combining so the key step here really is to combine the Harnack estimate and that entropy estimate to give an upper bound on the curvature. So key step is that, yeah, Harnack plus entropy imply a curvature bound. So bound on K. Okay, so how does that work? So now I need to explain to you how to integrate up the Harnack to get control on the Gauss curvature. So the idea is this. So let's suppose we have some point, let's say K, at a point, let's say x0 and a time t0, where well, so K, let's say this is, yeah, so on assume that the curvature at that point is the sup K at time T naught. And we're going to assume this is big, right? So there should be some point where the Gauss curvature has got really large, and we're going to try and get a contradiction to that. Okay, so let me call this sup K, we'll call, say, K, what do I want to call it? K bar. Right? So this should be just some large number. All right, so then first of all, we know that if I wait a while, then the curvature can't grow too quickly. So we know that ddtk is Laplace k plus 2k k minus 1. Okay, so this is no bigger than, say, Laplace k plus 2k squared. And so that means if I integrate the maximum principle would say essentially this is this last term will control how quickly the maximum grows. And in particular, you can see fairly quickly that I still have Gauss curvature bounded by, say, 2k bar, provided I don't wait too long, right? So provided the t minus t naught is less than or equal to, I think it works out to be 1 over 4k bar. Yeah. Okay, so on that time interval, we still have a kind of uniform control on the Gauss curvature. And that means we also have quite a good control on the geometry, right? So because we know that, so G, remember, is e to the 2u times G bar, and let's call this the metric at time t naught. And then we have du dt is, well, it's bounded by 2k essentially. And that's bounded by our what was it, 4k bar, maybe, something like that. Actually, so it's just a 1k, I think. Yeah, so it'll be a 2k bar. So that tells me that u at time t naught is just equal to 1. Sorry, equal to 0. Yeah. This says that u will be bounded by some 2k bar t minus t naught. Okay, and again, so if I'm looking just on this time interval here, this will be bounded by half. All right, and that tells me that the metric g, well, e to the 2u would be bounded by, well, what would that be? E to the half. So it's root e times g at time t naught, and greater than or equal to 1 over root e times g at time t naught. Okay, so yeah, so the curvature bound means that on this time interval, the metrics remain comparable. So I can really, I can work with just the metric at time t naught and really only lose the factor. Okay, so that's nice. So now what I want to do is, so here's t naught. Let's take the time direction to be vertical, and here's our, let's say, t naught plus 1 over 4k bar. That was the end of this time interval. Starting at this point, x naught, I want to see what happens when I sort of integrate along a curve to end up at some other point, x1. And I want to show that I can get a good lower bound on the Gauss curvature at that later point. Okay, so let's take, let gamma be a minimizing geodesic. Well, with respect to the metric at time t naught, from x naught to some other point x1. Okay, so that means that, well, we know, okay, if I parameterize this on, say, the interval 0, 1 into m, that means that the length of the tangent vector with respect to the metric at time t naught is just constant equal to the distance from x naught to x1, again, with respect to the metric at time t naught. All right, so now what I want to do is integrate d by ds log k along well, so what do I want? So let me call it gamma tilde of s is gamma of s at time t naught plus what was it, S over 4K bar. Okay, so if you like, this is just somehow visualize this would be something like a straight line along here. So moving through time at a constant rate and through space at a constant rate along this geodetic. Okay, so what do I get? D by ds log k. Okay, so I'll get one term which is differentiating in the time direction. So it'll be 1 over 4k bar ddt log k. Okay, and then the other term will be plus gamma prime in a product d log the spatial derivative of log k. Okay, and the Harnack tells me that, okay, remember the Harnack says that ddt log k is greater than or equal to gradient log k squared minus some constant. Okay. Doesn't really matter what the constant is here. So then this will be greater than or equal to, I get 1 over 4k bar gradient log k squared minus c over 4k bar. It's just a constant, don't care too much about that. And then plus, okay, this last term I'll expand out using Cauchy-Schwarz. So I'll get a, so minus one term which just cancels out that term I've got there, gradient log k squared. And the other term then would be, I would get, what is it, k bar times length of gamma prime squared. I think I've done that right. Okay, and this of course is just, so this would be minus k bar d squared. That's this d is this distance from x0 to x1 along in the metric at time t0. Okay, so then this and this will cancel, and essentially I get that. So log k x1 t0 plus 1 over 4k bar is greater than or equal to log k x0 t0. Well, that's log k bar, and then I get a just the integral of this from 0 to 1, which is minus k bar d squared and minus c on 4k bar. Right. Okay, so let me put that a slightly different way. It says that, yeah, so k x1, let me just call this t1 for simplicity, t1 is greater than or equal to k x0 t0, and I get a e to the minus, well, some constant times k bar times distance squared. Yeah, okay, so that's the estimate you get from the Harnack inequality. Okay, so what does that say? It says as long as I go a distance so that this k bar d squared is sort of controllable, then this exponential factor will be controllable, and I get that the Gauss curvature is still some fixed fraction of what it was at x0 t0. So this is k bar here. Okay, so now let me integrate that over. Okay, so it's going to be the ball of radius. So I want to take radius c over root k bar measured with the metric at time t0 about x0. Okay, so on this ball, on this region, we have this lower bound. So we get k is greater than or equal to some constant here, which is, it doesn't depend on anything. It doesn't depend on k bar, some constant times k bar. All right, now I also know okay, so that would be good if I had a lower bound on the volume, and I do have that because of the curvature bound. So k less than or equal to 2k bar tells me that I have a lower bound on injectivity radius Okay, so here I'm skipping over some geometric facts because I want to get to the punchline in the next 5 minutes. So we have a low bound in the injectivity radius. It'll be less than or equal to pi over, what is it, square root of 2k bar. Okay, so that means if I look at a neighborhood of any point of radius, less than this, then the exponential map will be a diffeomorphism. And in fact, the Gauss curvature control will tell me that I have a lower bound on the volume. Okay, so that says the volume of this set here. Let me call it something simpler rather than having to write it again. So this is A. Volume of A is greater than or equal to a constant over k bar. Okay, so the radius is like 1 over root k bar, and this is just saying that sort of it would still be comparable on this radius to the Euclidean volume of that radius. Okay, so now I can integrate. So that tells me that n is greater than or equal to, okay, so what is it? Integral over m of k log k. So this is greater than or equal to integral of a of k log k. And now k is bigger than this constant times k bar. Okay, so this would be c k bar log c k bar times the volume of A. And so that is, okay, so I get c k bar log c k bar and times c over k bar from the volume. Okay, so they can see now I needed that extra volume, that extra log part in order to get this control. So I end up with basically bigger than some constant times log k bar plus another constant. Okay, but now that's a contradiction. If k bar is large. Okay, because we know that n is not increasing, so n is bounded above. So because I have some upper bound on n. So given the upper bound on n, then this k bar can't be too large. And so that tells me that I have a uniform bound on Gauss curvature, independent of t. Okay, so that's sort of the what you get from putting the integral entropy bound together with this nice Harnack estimate. Okay, so where does that get us? So we could deduce here actually from just the compactness theory for Riemannian manifolds that our sequence of things converges to a nice limit, which is a soliton. Okay, and the reason for that is that now we've got a bound on the curvature, and of course we've normalized the area, so the total area is fixed. That gives us a diameter bound because of this injectivity lower bound, right? So so we have a diameter bound would be the next step. And that follows from everything we already know once we have this. And then we can use the Harnack again to give a lower bound on curvature. So Gauss curvature bigger than some positive number delta, strictly bigger than 0. And yeah, okay, so we have good control on Gauss curvature, and that's already enough to take a limit using the compactness machinery. That's not what Hamilton did. What he did was go back to these soliton quantities and look at this quantity, which is gradient I, gradient J F plus K minus 1 Gij. Okay, so let me call that Mij. Okay, so we haven't looked at that one yet, but that's actually the one that characterizes the soliton. And it's, well, I won't do the computation, but if you work it out, you get ddt length of m squared. So the sum of the squares of the components of this is, well, actually I'm going to throw a term away. So this is bounded by Laplacian length of m squared. I get a good gradient m squared. And then you get one extra term, which is minus twice Gauss curvature length of m squared. So this one is actually really nice in the positive curvature case. In particular, now that I've got this lower bound on Gauss curvature, then this is less than or equal to Laplacian minus 2 delta m squared, and that gives me straight away control. So m squared is less than or equal to a constant times e to the minus 2 delta t. Yeah, so this m decays exponentially, and that really gives me the convergence, because now if I look at the modified flow given by moving in the gradient f direction, ddt gij is minus 2 k minus 1 gij plus Lie derivative in direction gradient f of gij. I guess it's maybe minus gij. Yeah. Then this is just minus 2 mij. Okay, so that says that I get ddt of the metric under this modified flow is bounded by a decaying exponential. And from that, I get that it converges, that the gij converges exponentially to a limit, which is a soliton, right? Okay, so that's essentially Hamilton's argument. And the last step, of course, we want to show that it converges to constant curvature. And so the final step would be classify the solitons and show that they're spheres. Okay, so it should be only spheres. And Hamilton did that by quite a nice sort of complex analytic argument. But the drawback of his argument is that he really assumes the uniformization theorem. So he's assuming that it has the conformal structure of the sphere, and then you can do the analysis on the Soliton equation to show that the sphere is the only solution. And we'd really like to have a proof that doesn't use that, that really proves the uniformization using Ricci flow. So his argument doesn't quite do that. Right, so next time, I guess I've used up my time this week, but next time I'm going to talk about the argument that Paul Bryan and I have, which uses the isoparametric profile. So in fact, you can forget about everything I've talked about today, really. It's a totally separate argument, doesn't use potential functions or anything like that, but it gives quite a nice way of showing that the Ricci flow converges to the round metric. So yeah, thanks. I'll stop there.
Cool. Thanks, Ben, for taking us through some rather interesting arguments. Let's thank our speaker. Does anyone have any comments or questions for Ben?
Could I just ask a quick question? I'm wondering hey, your lemma on this general lemma for surfaces with positive Gauss curvature.
Yeah.
Is there sort of a well-known or simple analog of this for curves that makes the corresponding argument for curve shortening flow as well?
No, I mean this argument really relies on commuting derivatives, right? Have to commute derivatives to get a curvature term coming out. And on a curve, there's no way to do that, right? It's interesting enough, there is a nice argument that works in higher dimensions, right? And
okay.
so you get this, okay, where was my lemma? Somewhere down here.
Just here, I guess.
Yeah, right. So in higher dimensions, there's a more general inequality, but in particular, you get, if you have Ricci positive, then integral over m of Ricci inverse ij gradient f is greater than or equal to integral m scalar curvature squared minus Ricci squared. Essentially by using the same argument. And here you get equality if and only if it's a Ricci soliton. So I found that, but I have never found a use for that. So it's sort of an orphan inequality. It's begging to be used to prove something is a soliton, but I can't actually find anywhere where this comes up naturally, unfortunately. Yeah, so there's some intriguing things there.
Yeah. I was just thinking the one-dimensional cases, it looks a lot like Vertinger's inequality.
Yeah, it looks like Vertinger, right? That's right. I don't know. I mean, I couldn't find any way to do that simply because it certainly can't be the same kind of argument of commuting derivatives, unless maybe you think of the curve as the boundary of a region, and then maybe you could integrate over the interior and commute derivatives or something like that. No, I don't know.
Hey, I've got to go, but yeah, thanks.
Yeah, see you, Matt.
Any other comments or questions? All right, if not, let's thank Ben again.
Yes. Yeah.
We'll look forward to having you speak again next week, Ben. All right.
Hello. Yeah.
Thanks everyone for participating, and I'll see you next time.
Thank you. See you later.